So today I'm going to talk to you about the work that we are currently working on with a few colleagues, and that's about a meta-analysis on the substitution potential of wood. So to set a little bit the big picture in which that motivates me, this meta-analysis, I use this figure from the IPCC 2021 report that shows the almost the near linear relationship between cumulative CO2 emissions and global warming in the past and for the future scenarios. And so what this figure shows very well is the residual carbon budget. So that is the carbon that we can still emit until we reach the climate warming targets. So for example, for the 2-degree targets, we have a little bit less than 900 gigatons of carbon that we can emit. And we are currently emitting 40 gigatons of CO2 each year. So that explains very well why we have to put a lot of energy into stopping the carbon emissions. And to stop the carbon emissions, we're here today because of forest that is seen as one of the key levers to that direction. And Esther just showed how France tackles it. Here I'm showing another view on the same question. That's a publication by Elomina in 2021 that shows how forest is framed in European climate policy. So this is a number of policies that refer to forest given different objectives. So you see that forests are seen as a climate solution. It's the third object that forests are framed in forest policies, following the provision of wood and the contribution to bioeconomy. So basically, European policies are saying that forests will both help cool the climate and provide more products for the economy. So when we talk about forests, what do we talk about? We're talking about different types of forests: high stands, coppice, temperate, tropical. We're talking about different types of management, industrial or small scale. And we're talking about different uses, from timber, with this example of the world's tallest timber building, pulpwood, that can be also paper, and energy. So the question here with this context, the question I want to answer today, to address at least, is can an increase in wood use cool the climate? So basically, can we reconcile all the objectives that we give to wood use and to forest? And as sub-questions, we will look into why some studies give diverging results as to the carbon balance of wood, what determines the carbon balance of wood, and what practices, what management could have the most carbon benefits. And so to set up the methodology, I wanted to remind you of the different elements that we have when we calculate the carbon balance of the wood sector. So we have processes that happen in situ, that are in green. So you have the forest growth, the extraction of the wood, and the forest growth that happens again after the cut. And we have ex situ processes that are the production of the wood products, the operation of the services or products that have been produced, here illustrated with a building, and the end of life of the products. And at each of these stages, you can have emissions or sequestration of carbon. And usually, when we talk about how wood and forest can help us with climate change, we're talking about substitution. It's been mentioned in the previous presentations. So substitution, it means that the wood scenario, it's actually substituting for a reference scenario in which we would have used less wood or no wood at all. So here, with my illustration of a building, instead of a wood building, we would have, for example, a traditional steel and cement building. So here I'm going to go into a little bit more details of which processes I will consider later in the talk. So for the processes in the forest growth, we can have the soil carbon, the sequestration in the live biomass. For the extraction, that would be the harvest residues and the forestry emissions. For the production, would have the carbon storage in the products and the manufacturing emissions. And then we would have maintenance emissions and end-of-life emissions. Here I put in two colors, two types of carbon. In pink, the biogenic carbon fluxes, and in dark blue, the fossil emissions. So that's one of the elements of when we want to model the carbon balance of wood sector, which processes we account for. Another element that is important to set up this question is what is the difference between the two scenarios? How do we mobilize an additional wood? Is it through a change in silviculture? Is it through a change in supply chain organization? So for example, the wood is diverted from one destination to another? And is it through the use of a different technology? For example, heating with gas and heating with wood. And in the end, when you have all these elements, you can calculate the carbon emissions for each of the two scenarios. And if you know also the wood volumes that was used in both scenarios, you can calculate what we call the substitution. So that's the difference in carbon divided by the difference in wood. So you have the amount of how much carbon is avoided for each cubic meter, for each additional cubic meter of wood you're using. So what we wanted to do is to look at this substitution, this carbon benefit of using wood for the published studies. So what we did is a meta-analysis. So we started by a query in the Web of Science, where we looked for papers that were talking about wood, carbon, that had different scenarios, and that were using different types of models. So when we do a meta-analysis, usually we frame it with the PICO approach. So we're looking here at the wood sector models. We're looking at in these wood sector models that have in which we apply an increase in wood harvest compared to a lower wood harvest. And the outcome we're looking at is a change in carbon emissions. So here in the top left picture, you have the publication year of the publications that we found through our query. So that's so far we have processed 226 papers, but we still have some to add. So you can see the big increase in the last years. That's probably a mix of the interest of the community for this question and the general increase in scientific publications. Then you can see in the bottom figures a bit the structure of our database, what we have in it. So you can see that the studies focus on very different time horizons. So we have close to 60 studies that have a zero time horizon. So it's typically life cycle analysis that don't have a time horizon. And then we have medium-term studies and a lot of studies above 70 years horizon, with regional scales that are also very varied and quite balanced, except for local studies that are either static or more long-term. And we have a lot of countries and economies represented also. So here I'm going to present to you the figure step by step, because it's a bit heavy. So here we will have with different, so the three frames are looking at different processes that I showed you. So on the x-axis, you have the soil carbon, the live biomass sequestration, the harvest of residues, the emissions from forestry, product storage carbon, manufacturing emissions, maintenance emissions, and end-of-life emissions. So then on the y-axis, you'll have the percentage of the studies, the percentage of the substitution estimates that have been recorded this that account for this process. So, for example, here for all the pulp and paper substitution estimates we have, we can see that 100% of these substitution estimates account for the manufacturing emissions, and 80% account for the live biomass sequestration. We can also see that for the dynamics, is there dynamics in the model? We can see that we have also close to 80% of the data points that account for the dynamics of the biogenic carbon, and the same for the dynamics of the fossil. But, and that refers to the first talk of this second session, we have for this section of data, we have no paper accounting for the rebound dynamics. So rebound, it's the market feedbacks, the market-based dynamics, or the land use change dynamics. So for pulp and paper, it's not very interesting actually, because we have very few studies. But then it becomes more interesting with other types of wood products. So for example, here for timber products, what we can see is a big imbalance in the processes, in the carbon processes that are accounted for. We can see that timber studies focus a lot, 80% include manufacturing emissions, but less than 50% account for the in situ processes of carbon. And they account also less than 50% of studies account for the dynamics of carbon emission, carbon fluxes. For the energy data points, we have a more balanced picture with more than 50% studies that account for biomass, live biomass sequestration, and for manufacturing emissions. For studies that data points that look at that concern mixed products, so that means that they look at several elements in the cascading fluxes of forest. We also have more balance than we have for the timber, but we have the opposite effect with more studies focusing on the in situ and biogenic carbon fluxes with respect to the manufacturing emissions that are a bit less represented in the studies. And for the wood products that are upstream, so that's not really wood products, it's the wood when it goes out of the forest, but when the authors don't really describe what is done with the wood afterwards. Here we have also this effect, but it's more logical that we have a stronger consideration of the in situ processes. And for dynamics, except for timber, we have a similar consideration of the biogenic dynamics in the studies, but it's just the timber-centered studies that have a very low consideration of biogenic dynamics. Then we can also look at have the same figure for the mobilization strategy. So what mobilization strategy are the papers looking at? And here we see also a strong imbalance for all categories. So we see that timber-focused studies look mainly at a change in technology, a change in design. So typically a change in wood in building type, whereas mixed product look at the supply chain organization, and energy wood product types look at an increase in wood provision through cutting intensity or rotation length. So then if we look at how these different patterns correlate with each other, so here we calculated the correlation between the use of the different processes in the models. And what we can see is that we have two clusters, two communities, one with models that account for that have medium-term time horizons, regional scale that look at mixed products, and they include soil carbon, biogenic dynamics, harvest residues, and live biomass sequestration. So that's an approach that is concerned with medium to long term and that ecosystem centered. And then we have another approach where we have studies that look at manufacturing emissions but focus on local scale more on timber products and on at a static time scale. So here we see two research communities emerge. And these two research communities, now what we want to know is, do they find the same result when they look at the substitution, when they look at how much CO2 do we emit if we use carbon or if we don't. So for this, what I did is calculate for all the studies that match one of the two approaches, what's the distribution of the substitution they give. So here you have the substitution with the zero being here, and basically what it means, so when you have a positive substitution, if you remember the formula before, so if you have a positive substitution, it means that using more wood decreases the emissions, so using more wood is good for climate. And if you have a negative substitution, it means that using more wood decreases the climate benefits, increases the emissions, so use of wood is bad for climate. So when we calculate the substitutions for all these studies, that's what we find. So we find that the product-centered approach has a positive carbon substitution median with a lot of positive values, with a median at 0.66 ton of CO2 per cubic meter of wood used. Whereas the other approach, the ecosystem-centered approach, finds a negative carbon balance. The median of the studies is negative with minus 0.24 tons of CO2 per cubic meter. So here we see that the bias in the processes that are accounted for or not has an effect on the results of the studies. So the next thing we did is to wonder, so if we take into account everything, if we take into account both the live biomass, soil carbon, harvest residues, biogenic dynamics, and manufacturing emissions, if we try to remove this bias by having the best model, how much do we find? And the answer is that the median is now 0. So we find that there is no benefit of carbon, of using more wood with respect to carbon. So that here what we're doing is comparing all the studies that have this setup, this modeling setup, with all the studies having a different model setup. But we saw before there are different communities, so maybe they're just doing different things and we can compare them. So the next thing is to show you, so for some of the studies, the results are detailed in the publications. So we are able to disaggregate the data and to record them with different levels of processes. So that's what I'm showing you here. So here you still have on the x-axis the substitution with the 0 going from a positive effect of wood to a negative effect of wood to the left. Here I split the figure between the different types of wood use. And here you see one color is one study. So here you see for one study, so you know it's the same setup, the same model, the same configuration, but just accounting for one process or not, how does it change the evaluation? Also for the top line in each plot is when we're not accounting for the process, the bottom line is we're accounting for the process. And to the left you have, so I'm showing you for two processes for which we have interesting results. So for the live biomass sequestration and for the manufacturing emissions. So here what you see is that for the live biomass sequestration, when we account for it, so basically when we go from the top line to the bottom line, we decrease the substitution. In some studies by a long shot, and even in some studies we go from positive substitution to negative substitution. Whereas for the manufacturing emissions, if we don't account for it, whereas if we account for it, we're increasing the substitution, and also sometimes going from negative to positive emissions, like for example in Dugan 2021 for mixed products. So the effect that we showed before when looking at all the studies, it's even true when we look within studies. So basically, the interest in looking at this is that we can understand why there are divergences between studies. And the answer is that it depends on the perimeter we're looking at, because at some stages, we have an increase. We have a better carbon emission, better carbon balance in the wood scenario, and in other stages, we have a better carbon balance in the reference scenario. So if we want to, as a society, to decide on the best scenario, on what is the best use of our resource, we really need to look at the whole sector. And then another use of the database that we want to
Aude, it will be time to conclude.
Yes, that's good. It's my last slide. So here, if we look at which mobilization strategy has the best carbon balance, so here I only took the studies that are using all the best that have a complete model. And here you have the distribution of the substitution estimates for different types of wood mobilization. And you can see that the only strategy for mobilizing wood that has a positive mean, a positive effect, is the cutting intensity. And these studies, basically, they rely on using more residues from harvest. So these are my concluding points. So the importance of accounting for both biogenic carbon fluxes and supply chain processes, to have a whole sector unbiased approach. And when we do that, we find that there are no carbon savings by increasing wood use. And then the next steps are to look more into the impact of the drivers for extra mobilization, because they may also shift the carbon balance, since not all wood have the same impact. And then also we need to look at here, since I'm looking at substitution, I only showed you studies for which there is a difference in the amount of wood that is used. But there are some cases where the amount of wood doesn't change, but the carbon balance changes because there is a different use of the wood, a different, for example, increased lifetime of the objects, or stuff like that. Okay, thank you very much for the attention.